All right, welcome back everyone. If you're an EPC or MEP engineer, you know that today's explainer is diving into something literally every single industrial project relies heavily on. But, and here's the kicker, it's an area where we see critical errors happening all the time: seismic bracing components. By the time we wrap up today, we are going to build a highly practical, step-by-step component selection framework that you can take and apply to your job sites right away.
So, let's kick things off with a question that gets right to the heart of those massive project headaches. Why do seismic bracing systems actually fail? I mean, we've all been there, right? You're on site, something goes wrong, and the knee-jerk reaction is usually to point the finger at one faulty bolt or maybe a weak clamp. We just naturally assume some isolated piece of hardware gave out under the pressure. But is that really what's happening under the surface?
Well, our source material delivers a pretty shocking truth that completely shatters that whole preconceived notion. Check out this quote with me. Failures in mechanical, electrical, and plumbing systems, our MEP systems, quote, rarely trace back to a single bad part. Let that sink in for a second. That is a massive paradigm shift for a lot of engineers. If an entire suspended pipe system comes crashing down, it is almost never just one bad piece of metal from the factory causing the disaster.
So if it's not a single bad part, what exactly is it? Well, here is our roadmap for this explainer to figure that out. First, we'll uncover the real cause of failures. Second, we'll trace the load path. Third, interface and strut selection. Fourth, common mistakes and QA. And finally, standards and Xinma. All right, part one, the real cause of failures, looking way beyond that single part.
You know, we constantly see this really dangerous yet incredibly common habit of treating bracing as just generic hardware. Basically, grabbing parts off a shelf, tossing them together, and hoping they hold. But true engineering, it means adopting the mindset you see on the right, viewing bracing as a coordinated restraint assembly. You are sizing a completely cohesive system for a specific load path, a specific application type, and specific anchor conditions. It's not about disconnected parts. It's about the entire assembly acting as one single unit to actually absorb that seismic energy.
Moving on to part two, tracing the load path. Basically, what you got to do before you even think about opening a catalog.
Let's actually visualize this journey for a second. Imagine a massive, invisible physical force, like a heavy seismic vibration hitting your building. Where exactly does that kinetic energy go? Well, step one, it hits the MEP element itself, like the suspended pipe or the ductwork. Step two, that force travels directly into the clamp interface holding it. Step three, it moves down into the rigid strut channel. And finally, step four, it transfers safely right into the anchor and the building's main concrete or steel structure. Listen, if you aren't tracking this exact four-step load path from the suspended element all the way down into the structure, your whole system is basically just a shot in the dark. Okay, part three, interface and strut selection. Let's talk about matching your hardware to that path. Look at how pipe, duct, and cable tray bracing all require completely different clamp interfaces. I mean, it makes sense, right? A heavy, round pipe filled with water behaves radically differently under stress than a wide, flat cable tray. But here's the catch. Despite needing totally different clamps at the point of contact, they actually share the exact same strut channels and anchors down below. So you absolutely have to specify that unique interface at the top to protect the shared structure at the bottom. No one-size-fits-all clamps here, guys. And that understanding directly impacts your strut decisions. Single channel versus double channel struts. How do you actually choose? Well, it completely boils down to the specific corridor conditions of your project. Single channels? They might be perfectly fine for lighter, isolated runs where the load is minimal. But double channel profiles? They provide the immense torsional rigidity you need for those heavy, stacked corridor conditions, where you are juggling multiple, compounding load paths all at once. All right, on to part four. Common mistakes and QA. Let's talk about catching those fatal errors in the field. When you actually dig into the industrial project data regarding bracing failures, it always seems to boil down to one very specific number: 4. There are exactly 4 major installation mistakes that repeatedly plague these sites. Our source material points out that these 4 mistakes absolutely must form your QA checklist. Number 1, improper anchor embedment depths in the concrete. Number 2, incorrect torque applied to clamp bolts. Number 3, exceeding the maximum allowed strut spans. And number 4, mixing incompatible hardware brands within the exact same assembly. Honestly, if your inspectors aren't actively walking the site hunting for these 4 specific disconnects, you're leaving your project incredibly vulnerable. Catching these errors is exactly what guarantees your load path stays secure.
Finally, Part 5, Standards and Xinma, taking a look at true coordinated assemblies.
To really get a feel for how this is executed at the highest level, let's look at Xinma's manufacturing scope. They don't just churn out single, isolated parts, they manufacture the whole shebang. Comprehensive cable tray systems, busways, seismic bracing, and intelligent cable management solutions. And they supply these to some of the most demanding environments out there. Data centers, rail transit systems, massive industrial plants, you name it. Engineering a genuinely coordinated assembly really requires that level of massive, overarching manufacturing expertise.
And to pull off producing these complex systems, Xinma has to comply with 4 incredibly rigorous standards. We're talking about IEC 61537, NEMA VE1, BSEN 50085, and the GB 312151 standards. The point here is that coordinated assembly isn't just a flashy marketing buzzword. It requires strict, documented adherence to heavy-hitting international and national codes just like these 4. Because at the end of the day, that compliance is the only way you can mathematically guarantee your load path is actually protected. Which brings us to our final and probably most important thought of this explainer. I want to leave you with this provocative question. Is the bracing on your current project truly a coordinated assembly, or is it just a generic mix-and-match pile of random hardware? I really challenge you to take this new mindset. Step onto your job sites tomorrow and audit your hardware. Trace those load paths. Do not settle for single, disconnected parts. Demand a fully engineered system. Thanks so much for joining me for this explainer, and as always, keep building smart.